everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video we're going to be looking at complex numbers, actually of two different kinds, and addition formulas relating both to the circle and to the geometry of the relativistic hyperbola. So complex numbers are of course an important algebraic domain, but from a calculus point of view, the complex numbers are really just one possible extension of arithmetic that can be geometrically useful. So we want to put things on a more equal footing by having the relativistic or hyperbolic analogs of complex numbers getting closer to being on the same level with complex numbers. Okay, so circle geometry, typically the unit circle x squared plus y squared equals 1, is intimately connected with the algebra of complex numbers, which is very closely connected with addition formulas for circular signed areas. And notably, we're going to be talking about this, as we like to do, without any notion of angle, or in fact any transcendental quantities. That's the challenge, so that we're thinking about things purely in terms of a polynumber or maybe quotient polynumber point of view. Now, in analogy to this, there's a relativistic story where we look at the relativistic hyperbola with the equation x squared minus y squared, well, either equal to 1 or even minus 1. And then there's a corresponding algebraic structure, which we might call the red complex numbers. And we might call these original complex numbers the blue complex numbers. Okay, so it turns out that these red complex numbers then are intimately connected with addition formulas for hyperbolic signed areas. Now, what's happening here is that these two geometries here, one Euclidean, one relativistic, they're actually just two of a triple of geometries. So that's all explained in my theory of chromogeometry, which introduces this threefold symmetry into a planar geometry. We're seeing a facet of that here, but the point is that there's a third geometry floating around, which we'll also figure in our story, but not in today's video. Later on, shortly, in fact, it will be becoming even perhaps more important in some sense than these two. So let me remind you very quickly the usual story about complex numbers, the blue complex numbers, all centering around this sort of new object I, whose property is that I squared equals minus 1. And then what happens is that a complex number is something of the form a plus bi, where a and b are for us rational numbers, and that's naturally identified with the point a, b in the plane. And so that's maybe typically a complex number z. And the way you add them is component-wise like this, and the way you multiply them is essentially by using this rule. So that a plus bi times c plus di is ac minus bd plus ad plus bc times I. Then one introduces the complex conjugate, z bar. So if this is z, then z bar is a minus bi. And then we can introduce the quadrance of the complex number z, which is z times z bar. It's a difference of squares, and we get a squared plus b squared. So notably, the modulus, which is usually talked about in classical courses, the square root of a squared plus b squared, is going to play no role at all for us, okay? Because square roots are highly problematic theoretically. Okay, so the quadrance is the fundamental concept, and the actual main theorem in the subject actually goes back in some sense to Diophantus, who stated it not in terms of complex numbers, but there's an underlying identity here which is responsible for this crucial equation, which is that the quadrance of the product of two complex numbers, z times w, is the product of the quadrance of z times the quadrance of w. And just to reiterate, the modulus, or the so-called argument of z, which is some kind of angle, play no role, at least initially, for us in setting up this theory. Okay? So we're strictly in a rational setting here. Every number that's appearing here is a rational number. Now, there's an important modern way of thinking about complex numbers, which ties it more closely to linear algebra. And that is to identify the complex number a plus bi with the matrix, the 2 by 2 matrix, AB minus BA. So in this way, the algebraic properties of the complex numbers are just derived from the usual algebraic properties of matrices. And crucially then the associative and distributive and commutative laws of the addition and multiplication are just consequences of those laws for matrices. So we save ourselves a lot of work. And then in addition, this quadrance of a plus bi, which was a squared plus b squared, is just the determinant of this thing. And that makes the theorem that I mentioned almost obvious, because the determinant of a product of two matrices is the product of the determinants. So that's very natural. So we have one identification of complex numbers with 2 by 2 matrices. Then we have the more traditional geometrical connection with simply pairs of numbers forming points, which we can think of as being affine points. So this is powerful because the complex numbers then connect with geometry, intimately with Euclidean geometry, because the quadrants a plus bi equals 1 condition really amounts to a squared plus b squared equals 1. So we're really talking about Euclidean geometry where the unit circle figures prominently. Okay, so this is a nice extra way of thinking about complex numbers that clarifies a lot of things for us and actually makes the transition to the relativistic setting easier. So a lot of the content of a first course in calculus revolves around the geometry of the circle and also the geometry of a hyperbola. And there's a particular diagram here that really ought to be standard material for undergraduate students, but is generally not really taught. So it's very important. It harks back to the rational parameterization of the unit circle, which I'm always talking about, crucial kind of understanding. But it's a little bit more elaborate here, so I'm giving you a little bit more detail how to connect this rational parameterization also with complex number multiplication. So this makes clear the intimate connection between complex number algebra and this geometry centered around the circle. Okay, so here's our unit circle, x squared plus y squared equals 1. And we're thinking about parametrizing it. And I guess you know that the way we do this is we join the point -1 to a point with coordinate t in the y direction. Now in this case, we're thinking about everything being in the complex plane. So this actually is the number it, because we're thinking about this as being the complex number I. Okay, and then you join these 2 points, and then you get this second point on the circle, and that turns out to be 1 minus t squared over 1 plus t squared plus I times 2t over 1 plus t squared, if we express it using complex number notation. And let's call this e of t. So there is e of t right there. Now, algebraically, there's another way of sort of understanding what's going on here. If we take this line here and we look at a line parallel to it through the origin, then have a look at where that line meets the line x equals 1. Okay, so then this triangle here will be congruent to this triangle here. They're exactly the same. So this is 1 and this is 1. This is t or it. So this will also be t or it. So this point here as a complex number is 1 plus it. That describes the points lying on this vertical line. Now, if we take z and we square it, okay, square it in the sense of complex numbers, what are we going to get? We're going to get 1 squared minus t squared plus I times 2t. And when we normalize that point, actually geometrically, that's going to be up here somewhere in this situation. So there's z squared, it's another point on the plane. If we normalize that, dividing by quadrants of z, the quadrants of z is 1 plus t squared. So if we divide that, then it turns out that we get exactly the point that we started with over here. So that's another way of describing the rational parameterization of the circle. It's obtained by taking a point on this line, in this case z equals 1 plus it, and squaring it and then adjusting by the quadrants. So crucially, usually to get on the unit circle, we divide something by its modulus in traditional courses. But the modulus is a transcendental object. It's something that you can't get hold of because it involves a square root. Okay, so that's why we're doing this. We're squaring the thing first, and then we can just divide by the quadrants to get something that's on the unit circle. Okay. Now, geometrically, one way of thinking what that's happening there is that you're taking the point 1 and you're reflecting it in this line and getting that point there. This shows also, by the way, that actually it's really only this line that matters. You don't actually have to take this point on the line. If you apply the same formula with any multiple of z, well, then this ratio of z squared over quadrants of z is not going to change. So this point is really associated to this line. So what happens is that as we modify the line, the corresponding point moves around twice as fast. Okay, now the rational parameterization of the unit circle, that's what we have here. And now we can observe that if we have 2 points on this vertical line, say 1 plus it and 1 plus iu, if we multiply them, we'll get 1 minus tu plus it plus u. And then if we think about that, what that tells us, because of this formula here, is that e of t times e of u will be e of this thing. Okay, but it's really this thing normalized so it has the same form as this. So in order to normalize it so that it's on this line here, we have to divide by this first term. So if we scale this by dividing by 1 minus tu, we get 1 plus I t plus u over 1 minus tu. That's telling us that the multiplication of points on the circle can be described in these coordinates as e of t times e of u equals e of t plus u over 1 minus tu. This is the group structure on the circle. Well, there's a little bit of a problem with minus 1 because minus 1 has a special role in this story, so it's kind of excluded from this story. To include that, we would have to go to a projective setting, but we're not going to do that here. But anyway, this is an important formula telling us what the group operation is, and it's purely algebraic and rational. And crucially, it does not depend on any angles. Okay, so this is an alternative to the usual angular picture for describing the unit circle and what's happening on it. So this multiplication on the unit circle is capturing what's usually described in terms of angles, but it allows us to connect with some important formulas called addition formulas relating to areas of sectors of the circle. So here is our unit circle. Here is a quotient polynumber parameterization of it, the standard one. So gamma equals these two functions, 1 minus alpha squared over 1 plus alpha squared, and 2 alpha over 1 plus alpha squared. And then the corresponding addition formula relates these 3 signed areas. One at e of t, so t is some parameter, and e of t is this point here. And so the first one is from 0 up to t, so it's that signed area, that sector. The next one is from 0 to another value, say u. So from there, the first one is the red one, and the second one is the blue one. And the sum of these two is then the signed area of a third sector from 0 to, say, v, where this v is exactly that expression we've just seen, t plus u over 1 minus tu, that point over there in this situation here. So in terms of angles, this would be you're adding that angle to get this angle. But we don't have to use angles, and we don't want to use angles because they are transcendental things. They require infinite processes to deal with and to calculate with. Okay, so this is a rational kind of version of this story, but geometrically the content is the same, that this area here plus this area here is the total area determined from here to here. Okay, that big area there. Now, considerable care is needed here. So first of all, the thing is in quotes because I remind you, we actually have not properly defined what we mean by the signed area of such a sector of the circle. In fact, I'm trying to convince you that it's almost impossible to get an exact definition of that quantity. It's somehow illusory no matter what we do. But nevertheless, from an engineering point of view, we might want to know what the approximate relations are between these kinds of things. So this is perhaps interpreted as an approximate relation. Okay, so there's considerable care needed not just for that approximate aspect, but also because it turns out that the formula only works sort of in certain ranges. So that's because our parameterization has this difficult point that I've already mentioned. Okay, at -1, the circle is not actually parametrized. So it's safest if we restrict ourselves to, say, values t and u between -1 and 1, so that these 2 points that we're starting with are on the right-hand side of the circle. Then we don't run into any problems of sort of going across this boundary here. Okay, so we're touching base with some more sophisticated things. We're just taking an applied point of view right now. We are looking at these formulas and saying, okay, an engineer could use that to study areas on a circle. In particular, we have some control of not just the total area of the circle, but also sectors of the circle. Okay, so our theory is quite a lot more powerful than the old story of calculating just areas of circles by approximating polygons. Okay, so now let's introduce the red complex numbers. That's the same kind of story, except that we're introducing a new object called j, such that j squared equals 1. And j is not 1 or -1. J is some new object. Okay, so then, to a pair of numbers forming an affine point, we can associate this red complex number, a plus bj. Let's call it z. Then we can define addition of two of these things, component-wise in the usual way. But more interestingly, we can define multiplication of two of them using this alternate rule where the j squared is equal to 1. So a plus bj times c plus dj is ac plus bd, because the j times j is 1. And the coefficient of j is ad plus bc, as it is in the I story. So we might call these the red complex numbers, maybe denoted by something like that, or if you're working traditionally, c maybe with a small r underneath it. Okay, what about the rest of the theory? Well, you can define a complex conjugate, a minus bj. Then you can define the quadrants of z to be z times z bar. And that's also a difference of squares. But now we get a squared minus b squared, because the j times j is 1. And then it turns out that the quadrants of z times w equals the quadrants of z and quadrants of w. And the easiest way to appreciate that is to go back to this object and to recognize that you can identify that with another 2 by 2 matrix, A, B, B, A. So these red complex numbers also sit inside the algebra of 2 by 2 matrices, but in a different way from the blue complex numbers. Not better, not worse, just different. And then this thing here, this quadrant, is just the determinant, a squared minus b squared of that. And so this is just the usual product of determinant rule. But crucially, this algebra that we're getting is not a field, because there's other things besides 0 which are not invertible. In particular, the quadrants of 1 plus j, or the quadrants of 1 minus j, is 0. So these objects are not invertible in the algebra. So that means that algebraically it plays a little bit of a different role. And historically, complex numbers have been much, much, much more studied than these ones. But probably the playing field ought to be leveled. Okay? I think the case could be made that these are, in fact, just as important as complex numbers. Okay? Especially since we live in a relativistic world. that's the way modern physics explains the world. And so relativistic kinds of algebra are, just as potentially important as Euclidean ones. In fact, maybe even more so. Okay, so do not minimize the potential importance of understanding this red alternative to the usual complex number story. I want you to think about them as just being different, alternate algebraic domains in which we can do arithmetic. So for an important application of red complex numbers, let's study the relativistic hyperbola x squared minus y squared equals 1 from a point of view that wants to put that parallel to the usual unit circle. So here is the curve we're talking about, and we're interested in a rational parameterization of this. And we can proceed pretty well exactly as we did for the unit circle. We can start with this point minus 1. We can choose a point j times t. J is our special number, so just t times that, somewhere on this y-axis. We can join minus 1 to that and see where the other point of intersection is with the curve. So that turns out to be the point with coordinates 1 plus t squared over 1 minus t squared and 2t over 1 minus t squared. And in this red complex number world, we can represent that by this linear combination involving our new symbol j. And we can call this f of t. Notice it's very similar to the blue parameterization, except here we have a plus sign here and a minus sign there, and the other way around it's with a plus sign in the denominator here and the minus sign there. Now there's another way of thinking about this, which is entirely analogous to the picture I showed you for the unit circle. If we look at the line x equals 1, just as before, and choose the point 1 plus jt on it, so that's what you get when you take this line and move it, so it's through the origin now, but still parallel. Okay, so we're going over 1 and up j, or jt. And then you take that point z and you think of it as a red complex number and you square it. Okay, you're going to get some point maybe up there. And then you divide by the quadrance of that thing, just the same as we did in the other situation, and you get this point that we've already identified as being obtained through this construction. So this is another way of thinking about the parameterization. We take some line through the origin, we take some point on that line, we square it and divide by the quadrants, and we get a point on the conic. And in fact, that gives us an identification of lines through the origin with points on the conic, including also this branch here. Okay, so since if we have 2 points on here, say 1 plus jt and 1 plus ju, then the way they multiply in the red complex number story, we get 1 plus tu plus j times t plus u. And that gives us this formula that f of t times f of u, so the product of 2 points on the conic, will be f of t plus u divided by 1 plus tu. The appropriate scaling of this thing so that we get onto a point on this line. So this gives a group structure on x squared minus y squared equals 1. Again, with this point here somehow being excluded. Okay. And this is entirely analogous, and for relativistic studies, like if you're a physicist and you're interested in Lorentz transformations and understanding Einstein's special theory of relativity, this is exactly what you need, okay? This is exactly the kind of algebra that you need, this kind of group structure and the associated transformations of multiplying by unit vectors there. That's exactly what the Lorentz transformations or the boosts of special relativity amount to. So this is a very important picture, alternative to the blue story, especially for modern physics, but actually also for calculus, modern calculus. Okay, so now let's introduce an important definition that we've used already a number of times, but now we're going to put a name to it. So for a curve gamma, say p, q, usually with p and q being polynumbers, But now we're also thinking a little bit more generally. Sometimes P and Q might be quotient polynumbers, usually called rational functions. Okay, so we're going to define the signed area differential of this curve gamma to be, we're going to call it d of gamma, equals P dq minus Q dp. So this basic expression that appears in the fundamental theorem. So we're going to give it a name. We'd call that the area differential of the curve. So for some examples, if gamma is the usual power function, y equals x to the n, or described in polynumber form as alpha to the n, then d of gamma is n minus 1 times alpha to the n. That actually works for a general integer n. More generally, if we have a curve given by alpha to the m and alpha to the n, then the differential d of gamma is n minus m times alpha to the m plus n minus 1. It's a generalization of what's happening up here. Now, for the circle, so now we're extending our understanding here to having quotient polynumbers. Here's our standard rational parameterization of the circle, and we made this computation that basically amounts to that the differential of this gamma is 2 over 1 plus alpha squared. And now we're in a position to extend that calculation to the rational parameterization of the relativistic hyperbola. So if gamma is equal to 1 plus alpha squared over 1 minus alpha squared and 2 alpha over 1 minus alpha squared, that's exactly that rational parameterization of the hyperbola x squared minus y squared equals 1 that we've been talking about. Then a computation, which is very much like this one, is that the differential of gamma equals 2 divided by 1 minus alpha squared. That's a good exercise to check that. So these are very close, algebraically, very similar kinds of calculations, but geometrically, there's quite a big difference between these two things, especially if you graph them as, say, as functions of alpha. They will look very different. And so now, finally, I want to show you the corresponding addition formula for the relativistic hyperbola, an analog of the ones that we've seen for the circle. Here's our hyperbola again, and we can think of it as parameterized. Here, 1 plus alpha squared over 1 minus alpha squared, and 2 alpha over 1 minus alpha squared. And here are some points on the hyperbola, say f of t, f of u, and their product, f of t plus u over 1 plus tu. And the addition formula is that the signed area from 0 to t of gamma, so this red portion there, plus the signed area from 0 to u of gamma, that's the blue portion up there, equals the signed area from 0 to w of gamma, where w is this number t plus u over 1 plus tu. So in other words, the sum of these two is this bigger signed area swept out there. And again, we have a formula in quotes, so we don't have exact definitions even of what these signed areas are. And perhaps exact definitions are forever elusive. But nevertheless, there's an approximate aspect to this, but still considerable care is needed. In particular, you need to think about which values of t and u you're going to choose to ensure that you get a nice formula. So, for example, we could restrict ourselves to t and u being from minus 1 to 1. That effectively means that we're talking about t and u being on that branch there. Okay. So we've done quite a lot of things today. We've seen a lot of material connecting with geometry, making that transition from the Euclidean story to the relativistic story, and seeing that calculus bridges these two things, right? Calculus is not a Euclidean theory. It's an affine theory which can be applied to the Euclidean case, can be applied to the relativistic case. And we're going to see the importance of the relativistic side even more in subsequent lectures. So there's much to learn. I'm Norman Wildberger. Thanks for listening.